Let's review some of the hyperparameters we've discussed so far. One is learning rate, denoted by alpha. This is a hyperparameter that we've discussed as part of several prior modules. It defines the size or length of each step or the magnitude of each iterative update taken by gradient descent. In other words, it regulates the effect of each individual update, which we often refer to as delta, on the next iteration's parameter values. A larger alpha value means that the gradient descent will move more quickly but can be potentially less stable. A smaller learning rate means that the gradient descent algorithm will evolve more slowly. Weight decay, denoted by lambda, opposes excessive growth of parameter magnitudes, preventing a small number of high-valued or large parameters from completely dictating or having a disproportionately large effect on a model's behavior and performance. Weight decay allows gradient descent to observe the effect of more parameters on model behavior and provides an overall more robust description of the system behavior overall. The momentum hyperparameter is denoted by mu. Momentum smooths the effect of individual updates on a gradient descent path or trajectory, reducing the potentially detrimental effects of smaller scale topological features within our function space, as well as reducing the effect of noise on convergence and potentially making it more stable. Now, one thing we'll see is that momentum as a hyperparameter may be effectively paired with small batch or single element stochastic gradient descent in order to improve stability. To explain how momentum and dampening affect gradient descent for machine learning, we again begin with the most basic form of the iterative update expression it employs, as shown here. This is an expression we've seen a million times. The updated parameter array for iteration it is equal to its previous value minus the product of the learning rate and the delta value. Just note that when we consider momentum and dampening, the delta value is no longer equal to the gradient by itself. We then introduce a velocity value, which I often call a hyperstate, although I don't think that's a formal term. It's a value or state associated with our hyperparameters, and it's defined in terms of both the momentum mu and the dampening tau hyperparameters. So we can define the velocity value for iteration it, and there's two cases here. There's one case where the iteration is greater than 1, and then where the iteration is equal to 1. So I put here initial condition. That's a little bit misleading. The initial condition is iteration 0, so this would be the first iterative update. Now, for iterations greater than 1, the velocity value is equal to the momentum times the previous velocity value from the last iteration, plus 1 minus the dampening times the gradient of the objective function we want to minimize, evaluated for the parameter array at iteration it minus 1. Now, hopefully you can see why we need a separate case when it equals 1, because there is no previous velocity value to draw from. As such, the velocity for iteration 1, our first iteration, is simply equal to the gradient, again, of the objective function we want to minimize, evaluated for the parameter array at iteration it minus 1, which in this case would be 0. And we do have an initial condition, theta